And we're live.
Someday students on the internet are going to wonder who that mysterious voice is, but that's okay. So, this is from 12.2 in the textbook. We'll probably spend a couple of days looking at this. So part one, some of the main features of plate tectonics, the theory that explains both the fact that the continents drift, float, move around on the Earth, and why they do so. So to first understand this, you first have to understand the structure of the Earth. And I wrote here, complete the following from page 519 in your text. I'll fill this in, but if you're looking for better writing, if you have your text open to page 519, it'll be easier for you to follow along. You don't have to, but if you want to quickly open to page 519, you can. This is what we think the Earth looks like based on radar signals, based on the Earth's magnetic field, based on our best observational data. We haven't drilled down very far, so this is all second-hand inference, second-hand guesswork. Looks like this. First of all, on the outside, we have the crust. Its thickness is anywhere from 5 to 70 kilometers. That's the dirt, that's the gravel, that's the rocks, that's what you think of as when we're talking about the Earth's surface. But there's much more to it than that. We have the upper mantle and the lower mantle. So the mantle is the Earth's thickest layer. We break it into two parts, upper and lower. It's about, well, the two of these together, about 2,900 kilometers thick, about 3,000 kilometers thick. It's mostly solid, but the upper is partly molten and partly solid. The lower level is mostly solid. Then we have the outer core and the inner core. The outer core, we believe, is liquid. We think. We think it's a mixture of liquid iron, molten iron, and nickel. And we think that's part of what gives us our magnetic field that both deflects compasses pointing to the north, but also deflects a whole bunch of harmful cosmic rays that would normally kill us. The inner core lies at the very, very center. Inner core. It's mostly iron and nickel as well. It's very, very hot, but it's under so much pressure as well that we think it's solid. And our best explanation right now is that the inner core and the outer core are spinning, but they're spinning at different speeds, and that's what causes the Earth's magnetic field. If you're not sure how that could possibly cause a magnetic field, take Physics 12. In terms of distances, 1,216 kilometers, 2,270 kilometers, 2,225 kilometers, 660 kilometers, and then the crust. Well, the crust, very thin, like the skin of an apple. Doesn't make up much of the Earth. 660. If you combine the 660 and the 225, you get about 2,900. And again, it varies. We've drawn this all wonderfully symmetrically spherical. It's not the case. Close, not the case.
What's the third one?
Number? 660, 2225, 2270, 1216. And again, Emily, if you're studying, if you're trying to figure this, page 519 is where I stole this diagram right from there. So, each layer of the Earth has varying thickness and state, solid, liquid, etc. So if we fill in the layers, where do I have this information, Mr. Dewick, or are we just going to copy it from the chart that we did on the previous page? I think we are. Okay. First layer was the outer mantle. Its thickness was 660 kilometers. I got 5 here. I think I'm skipping the crust. Oh, am I? No, first one's crust. You're right. Good gosh, Mr. Dewick. Yeah, shut up and suffer. Crust. Yeah, that's preserved for the internet too. Crust. 5 to 70 kilometers. State. Solid. General composition, rock. Different types of rock, but rock. Then we have the upper mantle, about 660 kilometers thick. Sorry about that, folks. State, partly molten, but not uniform temperature and not molten everywhere. This is what causes convection currents, because the hotter areas want to flow towards the colder areas. Therefore, the continents on the top of them get dragged around and move. General composition of the upper mantle. Rock, iron, and magnesium. Then we have the lower mantle, around, on average, 2,225 kilometers thick. That's mostly solid, very dense. And again, the same composition, iron and magnesium, which is why we consider them both parts of the mantle, but we distinguish between the upper and the lower because the upper has liquid molten sections. Next we had the outer core and the inner core. Outer core was about 2,270 kilometers thick. It's liquid. And it's Fe and Ni. What's Fe? Iron. May as well do a little chemistry review since we're working our way towards the end of the year. Ni? Nickel. It's iron and nickel. Inner core, about 1,216, a very exact measurement. I'm not quite sure how they're that exact. I need to do some research. Kilometers thick. It's hot enough, in fact, it's about 5,000 to 6,000 degrees Celsius. It is hot enough that it should be liquid, but it's under so much pressure that it remains solid. So it's well past the melting point of, oh, and it's also made up of iron and nickel. The only thing I'm looking in the instructions, and it says beginning with the innermost layer to the outside. Let's cross out the innermost and let's put outermost and inside. We went from outside to inside instead of the other way around. If you're looking for a dumb way to remember it, CMC, crust, mantle, core. I think you'll be okay. Upper and lower mantle, figuring out which one is which, and inner and outer core, figuring out which one is which. The surface of the Earth is solid. But the crust is made up of tectonic plates. The crust is made up of tectonic plates. It includes the crust and the uppermost mantle, I guess, and ranges in thickness from 65 to 100 kilometers, give or take. Next is the, make sure I get this correct, Mr. Dewick. Why am I missing my notes on this? There's where I'm looking for. Here's the new word. I got to spell this. A-S-T-H-E-N. O-sphere. The asthenosphere. That's why I had to look it up. It's semi-liquid, and it allows the plates to move around. So it's semi-liquid. The reason we say semi-liquid, it is liquid, but it's really, really thick. Thicker than tar. It's like a really thick slurry. Because it's liquid, it has large temperature variations. We think those temperature variations are caused by pockets of radioactive elements, such as uranium, that as they decay, give off heat. This uneven distribution, this uneven heat distribution, leads to convection currents. Hotter materials in the mantle rise, and then they cool, and then they sink back down. And it repeats. So here's a cross section of the Earth's surface. We call this top section here above the asthenosphere the lithosphere. That's where what we think of the Earth's surface exists. So there's another word for you, the lithosphere, the top section. We have two main types of crust. We have continental crust. That's crust underneath land masses. And we have oceanic crust. That's crust underneath oceans. And what we find is this. So in the upper and lower mantle, we have all these convection currents. The heat will rise, cool off, and sink back down. And so right here, it would be dragging the crusts down and to the right. Right here, it would be dragging the crusts up and to the left. The convection currents, we believe, are responsible for the continental drift, for the motion of the tectonic plates. As the plates move, they can interact in several ways. Turn the page. from the page? Okay. First thing we can do is we can pull apart. The fancy word for that is called divergence. This is the term we'll use on your test. Divergent plates are areas where two continental plates or oceanic, two tectonic plates are being pulled apart by the convection currents. Does anybody know what the opposite word of diverge is? Converge. They can collide with one sinking under the other or both crumpling. We call this convergence. Hayden, going back to answering your question, there's two possibilities. One can sink underneath the other, and the other one goes on the top. Or they can collide with each other and both crumple. This is, in fact, what's forming the Himalaya Mountains. Okay. The third type is where they slide alongside each other. So they're not moving apart, they're not being pushed together, they're being pulled in opposite directions alongside each other. We call this a transform area. You can have divergence plates, converging plates, or transform plates. The region where they interact is called the plate boundary. So our goal today is we want to look at the three types of interactions and sort of figure out how they affect us. So the first kind is the divergent, the pull apart, the divergent boundary. The motion away from the ridge is called a ridge push. So you have some kind of a gap between two plates. It creates a value. And as it slowly gets pushed apart, we call that a ridge push. Except it has two specific names. In the ocean, we call it a spreading ridge. On land, where it happens more rarely, it's called a rift valley. A couple of examples here. So here is a rift valley. This is two continental plates being pulled apart. There is a large rift valley running through Africa, Kenya, and all those areas. It's a rift valley, huge rift valley, several thousand miles wide. Here is another example of a rift valley. I don't have any from under the ocean because you don't get good pictures down there. There is a very famous one, the Mid-Atlantic Ridge. It's an area that's being slowly pulled apart. So we're talking right here. What happens is you have molten lava bubbling up, and as it bubbles up and solidifies, it expands, it slowly pushes the rock apart. To have that happen, you need opposing convection currents on either side. So here's a convection current moving up and to the left. Here's a convection current moving up and to the right. And you have weakness right here, some kind of a hot spot in the asthenosphere that allows the molten lava to get through. Okay. We have convergent boundaries. And you can remember convergent, if you don't know what the word convergent, collide also begins with a CO. Convergent is where they collide. We have oceanic and continental plates. Where they collide is called a subduction zone. I think you turned the page. Where they collide is called a subduction zone. In my picture, here's a subduction zone right here. We have two plates colliding, and there's basically two possibilities. They can keep running into each other and pushing each other up and crumbling. That forms the mountain range. Or one can duck underneath the other one, and that forms what we call a subduction zone. Heavier oceanic plates goes under the lighter continental plate, pulling the rest of the plate with it. We call this a slab pull. This leads to lots of earthquakes and volcanoes. For example, there is a volcanic belt. We are part of a subduction zone. The west coast of North America has a subduction zone, and there is a volcanic belt right along the west coast of North America. Mount St. Helens, Mount Rainier. Mount Baker is an old volcano. I wrote down here, look on a diagram on previous page to find a subduction zone. So there is a subduction zone. There's a color picture in your textbook if you want to. You can make a little note next to here when you're studying. I stole this from page 522. So you can make a little note here. I don't, how clear is it? Is it in black and white on your notes? Still readable? Okay. When I cut and paste, it's not great. So, some convergent plates. It's going to work or not. Let's see. Have you guys got a screen at all? There we go. Okay, there's an example of an area where two plates are converging and they're pushing up together to form a mountain. I don't have a good picture of a subduction because that's generally in the ocean and under the ground. Sorry. So here is the convergence of an oceanic and a continental plate, and that produced the coastal mountains of BC and volcanoes. In fact, I think, oh, did I include pictures of a volcanic belt? No, I did that later on. Never mind. You can also have two oceanic plates colliding with each other. So the heavier plate will slide under the lighter plate. And you can produce an island chain. Enough of the lighter plate can get forced upwards that you might get a chain of islands. Japan, Indonesia, those are examples of island chains that were produced by an oceanic plate colliding with another oceanic plate. So the convergence of two oceanic plates can produce a volcanic island arc. The Aleutian Islands of Alaska is also an example of a two colliding plates. Two continental plates can collide. The edges fold and crumple, forming mountains, mountain ranges. Most famous of this, the Himalayas. They're getting a few centimeters taller every year because there is where two continental plates are colliding with a vengeance. So here's a picture of the convergence of two continental plates is gradually forcing the Himalaya mountains higher and higher. Turn the page. Transform faults. This is where plates slide beside each other. A famous example is the San Andreas Fault in California. Here's the problem. As the plates slide, well, you know what? Let me give you an illustration with a couple of rulers. So the problem we have with transform faults is the energy builds up, it builds up, it builds up as the plate moves, but the boundary itself doesn't, and then it releases all at once. Huge earthquake. So here's your transform plate boundary, the upper mantle, and the two plates moving side by side. That there is part one of continental drift and plate tectonics. That's what we think is going on. We'll talk about then how this leads more to specifically earthquakes and volcanoes, and we'll talk about types of volcanoes, types of earthquakes, types of earthquake waves in particular, and we've got a couple of cool videos to show you as well. For now, what's your homework?